Well, good to see you all again. Feels like a large amount of time since we've seen each other. So yeah, we've got a couple of things to tie up for the semester. So I hope, first of all, that you were able to kind of look through your exams and you're okay with how things were graded, but let me know if you have any questions about exams. Your homeworks have been graded up to the one that you haven't submitted yet. So all of your grades should be just about finalized, except for the last homework and the exam that we have left. Yeah, our exam 3 is going to be during finals week. So that's going to be our final is scheduled for Monday of finals week. So the first day from 2 to 4 p.m. is the time. So we'll kind of administer it the same way the others have been over Zoom. It is not a comprehensive final, so it's going to focus on the content that we've done since the last exam. So that would be problems from chapters 12 on functions and composition and inverses, as well as what we've been talking about with cardinalities of sets, countable, uncountable things. So I put some suggested problems up on Canvas this morning. So if you want some extra practice problems, feel free to give those a look. Yeah, so that's over here. Here's our webpage. Yeah, so a little bit of a lighter week this week. So we're just going to work on worksheet 23 today. Don't forget, you've got a homework assignment that is due on Wednesday night. And then on Wednesday, we'll just talk about the exam, what kind of things are going to be on the exam. And if you have any questions, we can go over that on Wednesday. So any questions as far as what the plan is for the rest of the semester, what work you guys are going to have to do?
Are you also gonna upload like the answer sheet for the practice problems to make sure?
So the problems are from the book, and they're all odd problems from the book. Yeah, so it's similar to the other exams. So that link is down here, and if you click on this, these are the sections that we've done, and they're all odd. And I also suggested some review stuff like direct proof, contrapositive proof, proof by contradiction, and induction. So although we didn't focus on those proof techniques, we were using those proof techniques in these chapters. So you are going to have to do proofs on the exam. You will have to use some of these proof techniques. So can't hurt to review some of those as well. Yeah, so Brandon asked, what did he miss from the first couple of minutes? Yeah, I just told everybody what the first 5 questions on the exam were going to be. So you'll have to catch up with that. Okay. Any other questions?
I have a question real
Yeah.
quick. For homework 10, after we submit it, are you going to have answers available for us?
Yes, I will put up answers. I don't think I will. I'll grade the last homework assignments myself. I don't know if I'll have them done graded by the time your final is. I'll hope to do that, but I'll put up the solutions on Thursday so that you can kind of grade your own work to some extent.
Thank you so much.
Yep. Anything else? So almost there. You guys have been doing great work this semester. One more homework, one more exam, and then you can relax. It's kind of weird getting this Thanksgiving break right before the real break. But yeah, anyway, I hope you guys got some relaxation and are ready to go for the last week. The last thing I want to mention, so yeah, you've got homework Wednesday night, exam next week. Please complete your FCQs if you haven't done so. So these are the course evaluations. Put the link over here. It's just your feedback is really valuable and important to me. So I'd like to hear from all of you. So maybe we'll stop a little bit early today to give you some time to complete that FCQ. Yeah. Okay, so any other questions before we get started with the material today? So we'll be working with this worksheet 23. Okay. Yeah, so before the break, we were talking about cardinality of sets, which are basically how many elements are in a set. Most of the sets we deal with are not finite, they have an infinite number of things. So we were kind of classifying, are there different types of infinities? So just a couple of things to remind ourselves of before we get started today. And so just a couple of definitions. So we say that a set, I'll just do these informally. We say that a set is countably infinite if there is a bijection f from the natural numbers into that set A. So this was kind of the definition we worked with last time. So we said a set is countable if it's finite or countably infinite. And what that means is it has the same number of things as the natural numbers. And in this definition, just recall that a bijection is a map which is a function which is both injective and surjective. So injective means one-to-one. Each element gets mapped to a unique output, and surjective is what we call onto, meaning everything in the codomain is in the range. So everything gets mapped to. So if we have a map which is both one-to-one and onto from the natural numbers to this set A, then we called it countably infinite. So that's just a little recap of where we were before we had Turkey. Any questions about that? Okay, so you can define countably infinite this way, or you can define it as like a theorem based off of the definition. But we talked about this a little bit last time. That is, if a set is countably infinite, that means we can arrange the items in that set in an ordered list. So for example, this is not too bad to prove. So this is an if and only if statement. So we can say kind of the forward direction first would be suppose that A is countably infinite. Then this would tell us that there exists a bijection from the natural numbers into and onto this set A. So then we're going to say we're going to let element 1 in set A just be what the image of 1 is under this map. And then we let A2 be the image of F2, A3, F3, and so on. So there's our ordering, right? We're just going to say the first element in set A is the element that 1 maps to, and so on. Any questions? if we consider the reverse direction, meaning now we're going to say, well, if the elements of A can be ordered, okay, then our map from the natural numbers into A, which is what we need in order to claim that A is countably infinite, then we're going to define a function f, which goes from the natural numbers into set A by saying and we get a map from that listing, right? We're just going to say the first element A1, we'll consider that the image of 1. The second element A2, we'll define that as what we get out of F when we plug in 2, and so on. And so since we have, I guess there are some details left here. And that is, you would need to show that this is a bijection, namely that if f of 1 is equal, or if that if we have two different inputs, then they should have two different outputs, as well as every element in A should be mapped by this map. And you can verify both of those properties about this map. Okay, any questions? Okay,
What is set A in this case?
A is any countably infinite set. So if A is countably infinite, then its elements can be ordered. If the elements of A can be listed, then that means it's countably infinite. So those go hand in hand. And then last time we did this proof where we kind of worked our way up and were able to show eventually that the rational numbers Q were countably infinite as well, which is a little bit counterintuitive, possibly, that the number of natural numbers is the same as the number of integers is the same as the number of irrational numbers. And so one way that we could do it, the textbook does it this way, which is a little bit different than the way we did it last time, is if we have this theorem up top, then right here, we just illustrate that we can weave our way through all of the all of the rational numbers in an ordered way. So for example, this would be A1, and this would be A2, and A3, and A4, and A5. And as long as we show that there's a path through all of these where we can kind of count them up, then it's a countably infinite set. And one thing to note here is when you're looking at these numbers, right, 1 over 1, that is equivalent to 1. So when we come over to like the column for 2, there's no element 2 over 2 because we've already counted that rational number. So we kind of avoid this double counting just by, if we've already listed that rational number, then we don't need to list it again, you know, for a non-reduced form of it. Okay, any questions? Okay, so that's a bit of a recap of last time. So here's a theorem that I'd like us to think about. So this theorem is saying, okay, any infinite subset of a countably infinite set is countably infinite. Okay, and that should make some sense here in that, okay, and that is if B is countably, I realize you're not seeing what I'm seeing. Reshare this. So if we have a set B, which is countably infinite, and if A is a subset of B, then what we're saying, what the claim is here is that A is countably infinite. That kind of makes sense, I hope, that if A is a subset of B, there shouldn't be more stuff in A than we have in B. Okay, so let me clear this comment out here. So let's come up with a proof of this claim. So let's suppose A is an infinite set. Sorry. Okay, so we've got our set A, and we're going to start with the hypothesis that this is a subset of an infinite subset of some countably infinite set B. And what I'd like to show is that A has to be countably infinite. Any thoughts here? My suggestion might be, let's think about using theorem 1 rather than thinking about finding a map from the natural numbers into this set. So by theorem 1, what could we say about one of these sets?
I think first we need to say that A is infinite and use the definition to support that.
So A is infinite. That's something that we are assuming. So we're going to assume we've got this, and then this is like an if-then statement. So it's saying if A is an infinite subset of a countably infinite set B, then A is countably infinite.
Well, if B is a subset of A, then every element of B is an A.
So we've got A is a subset of B in this case. So B is the thing that we know is countably infinite. A sits inside of B. We would like to show that A is countably infinite. So far I know, right, any element of A is in B. What can I say about B?
That B has elements that aren't in A.
It might, if they're not equal to each other. That's right. But we want to prove that A is countably infinite. We know that B is countably infinite. So if B is countably infinite, what could we say about set B? Independent of A, if we didn't even know that there was some other set A. B is countably infinite. What can we do with set B then? What does that tell us about set B?
It's a bijection.
There's a bijection. What's from where to where?
The natural numbers to set B.
Yeah, so by definition, there's a bijection from the natural numbers into set B. That's right. And as a result of that bijection, what does theorem 1 tell us that we can do?
That we can list all the elements of B?
Yeah, so that's right. So since B is a countably infinite set, exactly. Okay, so we have a list of elements in B, B1, B2, B3, etc. And so I want to prove that A is a countably infinite set. So to prove that a set is countably infinite, we can either construct a bijection from the natural numbers into A, okay, or we can use theorem 1 now and show that that some ordering exists. And so kind of these two bullet points up here are the difference between doing like a constructive proof where here's explicitly the map that's going to get that done versus I'm not going to tell you exactly what the map is, but I can show you that generally one exists by showing that we have some ordering of these things. So for example, this picture over here is like a non-constructive proof that the rational numbers are countable. We actually didn't say where 1 is going to get mapped to, where 2 is going to get mapped to with a formula, but we could show it with the list. So in this case, since we actually don't know what the elements of A are or what the elements of B are, it's going to be hard to define a map from the natural numbers into either of these sets. But I can show that a list exists, such as this one for A. How would that work? What would my A1 be? I'd like to show that there's a listing A1, A2, A3, so on. So if I can show that this exists, then we're done.
Is it just
B1.
A1 equals B1?
Possibly, right? So we know that A is a subset of B, right? So there's two cases. We have B1 over here. Either it's in A or it's not in A, right? It's possible that this doesn't sit in A. So we kind of just go through this list and we say, okay, if this is not in A, then we just skip it and we just list them in that order. So A1 would be like the first one of these that is in set A. And then A2 would be the next from the list of the B's that's in set A, and so on. So we can kind of just describe in words then how we can come up with this list. Yeah. So we're just going to go through the list of elements of B. And we're just going to skip the ones that aren't in A. Yep, and that's all we need to do there. As long as we can show that an ordering a list exists, then we know that that set is countably infinite. Since theorem 1 is an if and only if statement, so that goes in both directions. Okay. Any questions? So hopefully this is not a shocking. Some of these things are kind of weird, maybe that there's the same number of rational numbers as there are natural numbers. Probably not that surprising that a subset of something which is countable shouldn't be larger than it. It should also be countable. Okay. Any other questions about that? Okay. So couple of things just to go back and review. So here, this is saying cardinality. So this is what we just wrote earlier, that two sets have the same cardinality if there's a bijection from one to the other. And this is true regardless of whether these are finite or infinite cardinalities. We say the cardinality of one set is less than or equal to the cardinality of another if there's an injection from A to B. Okay, so if there's an injection, that means there's a one-to-one map. So that means that everything in A has its own unique element in B. So it would be impossible for B to be a smaller set, is basically what this is saying. And we get a strict inequality here. It's not as important if there's an injection, but a bijection does not exist. So this case over here is that this injection could possibly be a bijection, in which case we get the equality. But if there's an injection, but not a bijection, then we get a strict inequality that A's cardinality is less than B's. And this is what happens, for example, we can claim over here that, well, I guess we can't claim that yet. We'll see that the cardinality of the natural numbers, for example, is less than the cardinality of the real numbers. So we certainly have an injection from the natural numbers into the real numbers, the identity. However, what we would need to prove is that there's no such bijection that goes into there. So that's where we'll kind of work our way towards proving. Okay, why are the real numbers and the natural numbers different? So the real numbers are going to be an example of a set which is uncountable. And so we define uncountable as the negation of countable, right? So anything which is not countable, we would consider uncountable. Okay, so maybe here's something that is interesting. And that is, if we take open interval of numbers from 0 to 1, all of the real numbers in there, rational and irrationals, there's actually more numbers between 0 and 1 as there are all rational numbers everywhere. So in other words, the number of real numbers between 0 and 1 is more than the number of natural numbers that we have. Meaning we would like to prove that this interval is uncountable. So I'll walk through this proof. So this is a really, really famous classic proof in mathematics by Cantor, if anyone has heard of him. So Gregor Cantor was a mathematician in like the 1800s. He's pretty much the father of set theory. So he came up with this proof. He was the first person to prove that there are more real numbers than natural numbers. So that's kind of some interesting context there, that you might think that these are facts that people have known forever. This is about a 200-year-old fact. Not that old, relatively speaking. So we'll prove this by contradiction. Okay, so again, what we're trying to prove here is that this is countable. So we're gonna assume that this set, this interval, is countable. And then we'll show that we'll get some contradiction out of this so that our assumption should have been wrong. So we're gonna assume that it's countable, meaning that there is some bijection from the natural numbers into this interval from 0 to 1. Okay, so that function we'll call f. And again, we can claim this because our assumption is going to be that this interval is countable. And then we'll show that this is a contradiction. So we have a map from the natural numbers into this interval. So we're just going to say that ax is the image of this natural number x. Okay, so ax is now some number between 0 and 1. So it has some decimal expansion like this. Some of them might terminate, some of them go on forever because we're including the irrational numbers in here now. So ax1 is like the first decimal of ax. ax2 means the second decimal of ax, and so on. So these ax's are referring to, like, this is what we get when we take the image of natural number x, and all of these things are saying, well, it's some decimal that's between 0 and 1. Okay, so each of these numbers is something like 1, 2, 3, 4, and so on, since we're dealing base 10 here. Okay, so if the x maps to an irrational number, we don't have any issues about double counting things, since each irrational number has a unique decimal representation. Okay, that's not true for other rational numbers. So for example, the number 0.9 repeating is actually the same as 1. Have you guys seen that before? So we have a slight issue in things like this, in that although that's not quite an issue here because this would not be included in this interval, but there are non-unique ways of writing out the same rational number as we had with fractions. So we're just going to kind of avoid this double counting just by saying, if there are, these are going to be the two choices, we're just going to choose the one that has the zeros on the end. So what this means is that, right, f of 1, that's what we're calling a1, a2, a3, a4. So all of these numbers are in this interval from 0 to 1. And over here, we're just saying this would be the first decimal, second, third, so on. Okay, so we're going to assume that this function exists, and here's how we define it. And now what we want to do is get a contradiction. Why can't such a function exist? And so this proof is kind of what's called kind of like Cantor's diagonalization proof. So what we want to do, what we're going to show is that, hey, we're not hitting, this is not a bijection. There are some elements in the interval from 0 to 1 that we can't possibly get as an output out of this function. So the contradiction we're going to get is that hopefully if we can show that f is actually not a bijection, then we get a contradiction from that claim. So what Cantor did was he showed that let's create a number between 0 and 1, which is not on this list. So here's how he does it. He's going to say, let's pick a number y. So y is an element in the codomain. If this map is a bijection, then every element in the codomain should be in the range. So let's pick some number y and let's define it as follows. Its first decimal entry is going to be 9 minus whatever the first decimal was for our first number in the interval from 0 to 1. So by doing this, what we can see is the first decimal of this number y is different than the first decimal of A1, right? If the first decimal, I guess, unless A11, yeah. So no matter what A11 is, 9 minus A11 is going to be something different. So this would tell me that at this point, this number y couldn't possibly be equal to A1, right? Because their first decimal is off. And then we move over to the next one and we say, okay, this one, the second decimal of this number y is different than the second decimal of A2. So this tells us as well that y couldn't possibly equal A2, and so on and so on. So they work down, each of these elements and say, okay, the third decimal is different over here. So basically this number y doesn't appear on this list. It's different than every A1, A2, A3, A4, A5 that we can come up with. So therefore, y couldn't possibly be f of anything. Y is not in the range of this function. And that would contradict the claim that f was a bijection. Okay, any questions? This took a lot of really smart people a really long time to figure out. So it's okay if you have questions. This was not a trivial process. Okay, so now we've got our first uncountable set, 0, 1. The set of all real numbers between 0 and 1 is bigger than the set of natural numbers. So it is not countable. We're not very creative in our names in math, so we just call it uncountable. Okay, so here's a result which is pretty similar to the one that we saw with countable sets. Namely, we saw that like if the bigger set is countable, then any subset of it should be countable. And here what we're going to claim is that if I have an uncountable set, U, then any set that it is contained within should also be uncountable, right? So what we're saying here is it shouldn't be possible to take something which is not countable and put it inside of something which is countable. That would be a bit weird. I think my screen share has failed again. Okay, so let's prove this claim, and then from this, we'll real quickly get this result. So for those that aren't familiar with this term corollary, a corollary is something that follows immediately from a theorem. So like if we prove the theorem, there's really nothing to say to prove this. So this would be a result of, this would be a corollary of this theorem. Right, since this interval 0 to 1 is uncountable, and this is a subset of all of the real numbers, we'd be done at that point. Okay, so let's prove this theorem, and let's prove this one by contradiction. So for a proof by contradiction, we've got an if-then statement. So remember that if we're going to prove an if-then statement by contradiction, then what we do is we suppose the hypothesis is true that U is a subset of A, And we're going to claim that U is uncountable. So we assume that the hypothesis is true and the negation of the conclusion is true. So in this case, we're going to suppose we have this uncountable set U, which is a subset of A, and A is itself not uncountable. So I'm going to write with a double negative there. But that's okay. And let's hope that we get some contradiction here. Okay, so since U is uncountable, okay, first of all, it has to have an infinite number of things. If it had a finite number of things, then it would be countable. And if U is infinite and it's a subset of A, then A has to be infinite. Okay, so we know that A has to be infinite. And again, we already assumed that it was not uncountable. So in other words, we have assumed that it's countable. So now we have that A is a countably infinite set. Okay, it's infinite because by assumption U was, and it's countable because we're trying to prove this by contradiction. Does anyone see the contradiction?
Didn't we just prove that if something is a subset of a countably infinite set, then it must be countably infinite?
That's right. Yep. So this is a contradiction by this theorem right here. So remember, we just proved that any infinite subset of a countably infinite set has to be countable. So what we've got at this point in the proof, A is countably infinite. But since U is a subset of A, by theorem 2, okay, which is our contradiction. So once we reach our contradiction, there we go. The original statement was wrong, is false, so its negation, which is exactly theorem 6, therefore should be true. And so to prove this corollary, we showed that this is uncountable and this is a subset of the real numbers. So therefore, the real numbers are uncountable. Okay, so we have different types of infinities. Okay, in very non-intuitive ways, I might think. At least it was not intuitive for me, how all of these things work. Any questions? Okay, so now let's see how this stuff gets butchered in movies. So has anyone read the book or seen the movie, The Fault in Our Stars? I think, yeah. So it's a sad movie, but it made me cry for this scene alone. So yeah, for those that are not familiar with it, it's a really sad story about a young guy who gets cancer and he passes away. He's the guy in the wheelchair. And his girlfriend here is giving the eulogy for him. So here's her eulogy. I hope that you guys can hear the volume on this. Let me know if you can't hear the volume.
But I do know
Is that good?
this. There are infinite numbers between 0 and 1. There's 0.1, 0.12, and 0.112, and an infinite collection of others. Of course, there is a bigger infinite set of numbers between 0 and 2. Or
That is wrong, by the way. There's the same number of infinite numbers between 0 and 1 as there are between 0 and 2. But go on.
between 0 and a million.
Also wrong. There's the same number of numbers between 0 and 1 and 0 and 2 and between 0 and a million.
Some infinities are simply bigger than other infinities.
That is true. Infinities are bigger than other infinities, but the examples that she provided were not correct. Yes.
A writer that we used to like taught us that.
Okay.
You know, I love more numbers. That I'm like,
I don't know. I saw this part of the movie and my nieces were crying and I'm like, I know they're messing up the math. And they're like, no. Yeah, so just be careful about that. I think that the author was coming from the right idea. He must have read somewhere that there are different types of infinity, but he did not read very deeply beyond that part of it. So there are different infinities. If she had said, like, we have the natural numbers and we have the real numbers, that would have been a much more moving eulogy in my mind, but that's okay. Okay, so sorry for that digression. I just had to share that because it's not often that you see movies talking about different types of infinities. So I got so excited when they started it, and then I very quickly started to cry because they got it wrong. Okay, so let me, yeah, let's kind of think about this one, yeah. And then we're just about ready to wrap things up for the day. So here's a claim. So when we take a set A, any set A, doesn't make a difference. That's totally wrong. Yeah, I'm sorry. Then what we're saying is that the cardinality of the power set of A is bigger than the cardinality of A. And maybe that's not so clear. It should be very clear if A is a finite set. Certainly the power set of A contains more things. What's not necessarily clear is that when A is infinite, if A is countably infinite, and then we take the power set of A, why do I get something which is uncountable? Something different. So the proof is sketched out here. I don't know. I'll kind of leave that aside for now. We can come back to this if you're curious about this. But it is true that the cardinality of the power set of A is strictly bigger than the cardinality of A. And so from this, we do get a whole infinite ordering of infinity. There's an infinite number of infinities. Starting with the smallest infinity is what we call Aleph 0. So that's like the countable infinity. Okay, all of these other infinities are bigger than it, so all of these other infinities are uncountable. So all of these sets would have an uncountable number of things, but there are even orderings of uncountable things. So it's not, there's countable infinite, uncountable infinite, but not all uncountably infinite things are the same. So one thing that the book proves, I'm not going to get into it because it involves a bit of additional stuff that maybe it's not great to pile on at the end of the semester. But if you're curious, this is done in section 14.4, which is they prove that the cardinality of the reals is the same, there's the same number of real numbers as there are sets in the power set of the natural numbers. You can imagine how that theorem might go. It's a pretty heavy theorem. But we have kind of our first infinity is called Aleph 0. And then our next infinity would be Aleph 1, and that's how many real numbers there are. So this would be kind of the smallest uncountable infinite thing that there is. We would call this thing over here, these are Hebrew letters. This would be Aleph 2, that's Aleph 3, and so on, so on. And there's no end to this. So infinity behaves really, really strangely. And to really appreciate this, this is also in section 14.4. There's a conjecture, meaning there's a claim, we haven't proven it or disproven it, that there's no infinite, no type of infinity between the natural numbers and the real numbers. So there's no set whose cardinality, which is uncountable, but is less than the real numbers. And this statement is actually true and not true. We don't know about this. So this was a conjecture from Cantor, like the 1840s, if anyone's curious about kind of the historic context here. And then in 1900, turn of that century, there was an English mathematician named David Hilbert who came out with his 23 problems for the next century, meaning these are the 23 problems that I think we're going to be able to prove in the next 100 years. He had 23 of them. If you prove one of them, you get $1 million. There's a committee that oversees all of this. I'll say, if you want to earn $1 million, that's the hardest way to earn $1 million, I would probably say. There's been a lot of people that have been thinking about these 23 problems for a very long time. But every so often, one of them gets knocked out, and all of us mathematicians get really excited. And so this was one of these 23 problems of the century, was trying to prove this. And so Gödel tried to do this, for anyone that has heard of him, very famous set theoretic mathematician. So in the 1930s, not that long ago, he proved that either this statement is false and we're unable to prove that it's false, or this statement is true, but we cannot prove that it's true or it's false. And that has remained. So I guess we can kind of end things by saying, like, there are still some statements that we can't prove or disprove, which can get frustrating for mathematicians. So Gödel came along with some really surprising results about, yeah, there's no way that we're going to ever be able to discover all of the truths in the world, that there are going to be some things that are true that we're just not going to be able to prove that they are true. That's his incompleteness theorem, if you've heard of that. And so the nice thing about this hypothesis is, whether you believe it or not, it doesn't affect any other proofs anywhere else. So whether you accept this or not, you can go about your life doing set theory. And if I'm someone that believes the continuum hypothesis is true, and mathematician B, she says that it's not true, me and her, we're never going to get in each other's way. It's not going to cause any inconsistency. So that's the best that we could do, is like, we can't prove whether it's true or false. And even if we could, it wouldn't make a difference. So let's just move on. And that's what we decided to do with that. Yeah, so I think I'll stop here with something that we are not able to prove true or false. Okay, so with the remaining time, I thought that I might just kind of go through something in case there were some questions on the homework. The very first homework problem, I wanted to just make sure that people were kind of moving in the right direction on that one. And then I'm happy to kind of answer anything else that you might be considering. But the problem that I'm referring to is going to be pretty similar to this one. So question 1, write it up here, is trying to show that we've got this map F, which is going from Z5 into Z5. Which is defined by saying F of A is equal to 2A plus 3. And so question 1 on your homework asks you to prove that this map is well defined, and then show that it's, and then think about whether it's injective or surjective, and so on. So I want to kind of think about the first part there, which is like, how do maps like this even work, which is important to think about before we can start to consider whether it's injective or surjective, or both. So here's kind of a similar one, just to motivate it. So instead of saying Z5, I'm going to say Z3 to Z3. And what's important here is that Z3 is a partition of Z. So it contains 3 sets, 0, 1, and 2. Right, so equivalence class 0 would be all things that are divisible by 3. I don't know why I only picked positive ones, but you could put plus or minus in front of those 2. And then the equivalence class for 1, this would be things like 1 and 4 and 7 and so on. Right, so basically we're dividing all of the integers into 3 sets. Okay, all of the things that are divisible by 3, all of the things that have remainder 1, which would be all of these, and then all of the integers that have a remainder of 2 when we divide by 3. And so what would be really bad for a map like this to do, it shouldn't depend on the representative that we pick. So if I pick 0 from this set as my representative, and I think about where it gets mapped to, right? What we'd like is all of these elements in this set should all get mapped to the same equivalence class in the image. So I can't re-scramble up my integers, if that makes sense. So all of these things over here should all get mapped to elements in the same equivalence class. And all of these elements over here should all get mapped to the same equivalence class, and so on. So it would be really bad if f of 0 went to 1, and f of 3 went to 2, and this went to 0, because 0, 3, and 6, they're all in the same equivalence class. This map should send them all to the same equivalence class. So just to kind of check how that would work, so the map I'm suggesting here is take the representative of the class and square it. So in this case, we would have this would get mapped to 0 squared, which is 0. It doesn't have to get mapped to the same place, okay? What's important is that two different elements in that equivalence class should wind up in the same equivalence class. So it would be really bad if this equivalence class was different from this equivalence class. But because we're mod 3, right, 0, 3, 6, 9, they're both in the same equivalence class. So that would be fine. So here we see that 0 maps to the 0 equivalence class. This maps to the 0 equivalence class. This technically goes to 36, but 36 is divisible by 3, so that also is in the equivalence class 0. So that's the idea there about how this works. So if I wanted to prove this more generally, so this would be something that would be like applicable for part A of question 1 on the homework, then and here I'm of course not doing your homework problem, I'm doing this kind of similar one. What we want to start with is, let's say I've got two things such as 3 and 6, but I'll do this more generally now, that are in the same equivalence class, but are not equal to each other, right? So that would be like 3 and 6, 0 and 9, whatever. And what I'd like to show is that both of these things, their image is in the same equivalence class in the codomain. So one way to re-express the fact that these two things are in the same equivalence class mod 3 would be to say that A and B differ by a multiple of 3. And you can see that's true for all of these values up here. Add 3, add 3, add 3, so on. So if two things are in the same equivalence class, when the equivalence relation is mod 3, then they differ by something which is a multiple of 3. So I'm able to claim that B is equal to A plus 3K because this was my assumption. And I should say over here that this is some K in the integers with K not equal to 0 because we claimed that A and B are different from each other. So then let's see, okay, let's see what would happen to B squared. So B squared, right, that would be A plus 3K squared, which is A squared plus 6K plus 9K squared. Okay, which we can write as A squared plus 3 times an integer, factoring a 3 out from each of these terms here and here. So now this tells me that A squared and B squared have to be in the same equivalence class mod 3, since they differ by something that is divisible by 3. And that's what we wanted to show there. So this would be like a proof that no matter what element we pick as our representative from the equivalence class, it doesn't make a difference since every element in the same equivalence class is going to get mapped into the same equivalence class in the codomain. Okay, I don't know if that helps if you got stuck on that one or not. But otherwise, I'll stop here for today with the intent that you've got 10 minutes of your life that I'm graciously gifting to you. Please complete your FCQs if you haven't done that. That would be very much appreciated. But otherwise, if you have any other questions about homework, you're welcome to stick around. I've got office hours tomorrow from 1:30 to 2:30. And yeah, otherwise, if there's anything in particular that you'd like to discuss on Wednesday, we're not going to do anything new on Wednesday. Just do whatever I can to help you get ready for the exam. Just shoot me an email and just say, hey, would you mind doing this on Wednesday? And I'll do my best to accommodate everybody. There are some practice problems up, but yeah, we can kind of talk more generally about the exam on Wednesday. So this, again, the third exam is not, I'm not calling it a final exam because it's not comprehensive. So it counts as much as your previous 2 exams. And it's going to really just focus on functions and cardinality, that kind of stuff. But as you saw today, that means you might have to do proof by contradiction, contrapositive, direct proof, induction. You're likely to see these proof techniques. So definitely review them in general as well. All right, I talked a lot today. How is everybody doing? Okay. Okay, I think you guys are doing great this semester. Almost done. So keep it going, keep up the hard work, and yeah, we'll meet again on Wednesday. And yeah, good luck finishing up your homework in the meantime.